So,
so Stokes theorem. What's the basic objects we are concerned here? Okay, so in Stokes theorem, there is a surface with boundary as a closed curve. Okay, and also we mentioned about orientation about both of these three objects. So on the curve, we have a certain orientation, and this orientation will determine the normal direction in a surface by the right-hand rule. Right? So if you follow the orientation on the curve, and you use your right hand, and your thumb is going to point to the normal direction. So this is going to give me the normal direction here. Okay. So two geometric objects related by interior and the boundary. So in here, S as the surface is the interior. The boundary is the closed curve right here. And Stokes theorem says if I have a vector field, and of course our vector field here is going to be three components. Right? So the surface and curve are both in the three-dimensional space. And Stokes theorem says the line integral on the boundary. Okay, so this is the line integral on the boundary. It's going to be equal to the surface integral in the interior. Surface integral of the curve of the vector field. Okay. So this is the Stokes theorem. One more time, I want to mention in the very beginning of the chapter. So I said our main goal in this chapter is to establish the fundamental theory of calculus. Right? So in fundamental theory of calculus, we always want to link two integrals. One integral is in the interior, the other one is in the boundary, right? But you have to be super clear about what are those integrals exactly. Integrals of what function, and this integral is taken on what the geometric object. Right? So every time we talk about an integral, there is the domain where you're taking the integral, and also the function you're taking the integral. Right? So on the boundary, the domain is the curve. The integrating function is the vector field, where in the interior, the domain is a surface, and the integrating function is the curl of the function. Okay, so this guy is the curl of the function. So just to make it even clearer, this is nothing but a curl of the vector field, and a lot of people prefer to write it in this form, okay, which is exactly of the same principle. So these two are just two terminologies of the same surface integral, okay? So curl dot with the normal on the surface is the same thing as curl dot product with the surface element, okay? So these two are two slightly different notations. And if you still remember what we did for the line integral, we also have a couple of different notations. One reason I want to mention this notation is because I'm not writing the final. I'm not the one to write the final. So in case in the final you're looking at different notations, you should be able to tell what they are. Okay, so for the line integral, we also have slightly different notations. So on the curve, this is equal to the inner product between the vector field with the tangent, right? And this is the same thing as inner product between f dot with the tangent vector is nothing but the derivative, right? So dot with r prime ds. Okay, and if r as the curve definition is equal to xt, yt, and zt, then this r derivative is nothing but dr, dx, dy, and dz. So this can be also written down as the inner product between x, y, fgh with dx, dy, dz. So this is also equal to f dx plus g dy plus h dz. Right? So in the two-dimensional case, we only have these two components, f dx and g dy, for the circulation line integral. But in three-dimensional space, we also have this h dz component coming out. Okay? So essentially, we have one equation, but a couple of more notations here. Okay. Now let's stress again. This is about the surface integral in the interior, which is equal to the line integral on the boundary. This is gonna be our fundamental theory of calculus, version 1 in our grade. Okay? So this is our fundamental theory of calculus, version 1 in our grade, which is Stokes' theorem. So fundamental theory of calculus in R2, what is that theorem? What's the fundamental theory of calculus in R2? What is our previous theorem we studied? Green's theorem, right? Green's theorem in R2, you have a boundary of a region on xy plane, which is actually a closed curve, right? So the double integral in the interior is a double integral. And you have the line integral on the boundary, which is the line integral on the boundary, right? So that's the fundamental theory of calculus in R2. In fundamental theory of calculus, I want to quickly remind you, which is nothing but Green's theorem. Green's theorem in R2 has two versions. One is, if I take the, so basically this is our geometric relation. So we have a curve and we have a region. So if we take the circulation dr, this is going to give us a double integral of g of x minus fy dA, right? So this is one of them. The other one is if we take the flux, this is going to give you a double integral of g fx of gy dA. Okay, so this is the fundamental theorem of calculus. So in R2, there's only one fundamental theorem of calculus, which is the Green theorem, but you have two versions, which is about the circulation, and the other one is about the flux. Okay, in R3, we have two versions as well. One is Stokes' theorem, we talked about it in Monday's class. The other one is the divergence theorem, we're going to talk about in a minute. Okay, so there are two fundamental theory of calculus in R2. There are two fundamental theory of calculus in R3. Okay, so I'm very proud to present you my study guide. Okay, I like it very much. It's only 10 pages long, and I have only 10 pages long, but comparing with the online homework questions as well as the textbook, this is like the most concise version I can come up with. And I give you 6 key points in chapter 13, 6 key points in chapter 14, and 10 key points in chapter 15. And in chapter 15, the key points are, in some sense, scattered. So there are all kinds of terms and all kinds of new terminology you have to remember. But I did give you 10 points which you have to remember. Particularly the 3 major theorems, Green's theorem, Stokes' theorem, and divergence theorem. You should be absolutely clear about what they are essentially talking about. Okay, you should be absolutely clear about what they're essentially talking about. And in the final and in next week's test, you're definitely going to see those. So Green theorem, remind you again, is talking about fundamental theory of calculus in R2, which will connect double integral in the interior and a line integral on the boundary. Stokes' theorem is fundamental theory of calculus in R3, which lines the surface integral in the interior and a line integral on the boundary. Okay? So basically, there are several different versions of fundamental theory of calculus for a very good reason. Okay? Because in Cal 3, we're talking about calculus in R3. So fundamental theory of calculus to link integral in the interior and integral on the boundary, these geometric objects are much more complicated, and you have much more different varieties comparing to the one-dimensional case. In one-dimensional case, you just have one interval and 2 boundary points, and that's it. You don't have any variety to talk about this. In multi-dimensional case, you have so many different geometric objects with the interior and on the boundary. So naturally, you're going to have more versions of these theorems to come out. So last lecture, we were practicing Stokes theorem, and we were at Calc. So the surface is given by x squared plus y squared plus z squared is equal to 9, and also it is above z is equal to 2 square root of 2. Okay, so this is the problem we discussed. We compute the line integral on the boundary already. Okay, so if you still remember the sketch of the picture here. So this is a piece of a sphere. Right, this is a piece of sphere. It stays above z is equal to 2 square root of 2, which is a horizontal plane. And it is in a piece of a sphere, which is a sphere centered at the origin with radius 3. Right? So you use this plane to cut it through, you get this surface, and the closed curve is this boundary oriented in a counterclockwise direction. Okay? And the normal is going to be pointing upwards. Okay? Normal is going to be pointing upwards. So before we actually recall what we did last lecture, I want to quickly give you one observation here. So in this Stokes theorem, if the vector field is conservative, we have several different equivalent criteria for a vector field to be conservative. One of the most important things which you can actually use to check is if this guy equals 0. Right? So if a vector field is conservative, the most convenient method to check is to check its curl vanishes identically. Okay? Because for any given vector field, you can always compute this 3×3 matrix. If this 3×3 matrix is identically 0, this guy is going to be conservative. So this is identically 0, so the surface integral is identically 0. So the line integral of a conservative vector field along a closed line is always equal to 0. Right? But that's not the news to me. That's not news to you either. Right? In the very beginning, when we talk about conservative vector field, one of the most important properties is that the line integral along closed curve is always equal to 0. Right? This is one of the properties you may not be able to use it to check whether a vector field is conservative, because you have to check all the closed curves in order to verify it is indeed conservative. So if you want to use a method to check a vector field is conservative, this is the way to go. But once you check it is conservative, any closed curve, any line integral, as long as it's conservative, has to be equal to 0. Now with me? Mm-hmm. Okay. Now I want to quickly see, we actually did this on Monday's class. We did quickly check this guy is not conservative. And we actually also compute the curl of the vector field. So you should be pretty sensitive about this notation. This is saying nothing but the curl. Right? It's saying nothing but the curl. We actually did compute this to be -2, -2, and -2. Okay, so this is the curl, which is not identically 0. Okay, and we also compute the closed curve line integral here. It is equal to -2 pi, which is of course not equal to 0. Right? The vector field is not conservative. And every time, if we want to compute a line integral, the key step is to set up the parametric equations for the curve. Right? So last class we did set up the parametric equation for this curve. And one thing I want to stress, actually it's pretty easy to find a relation between x and y. Right? You plug in this condition into this equation of the sphere, you get x squared plus y squared plus 8 is equal to 9. So you get x squared plus y squared is equal to 1, which defines this circle. Right? So you do have a cosine t, sine t. A cosine t, sine t with 2 components are only going to define a circle in R2. This is a curve in R3, so I also have to have the z component. The z component here is given by 2 square root of t. All right? Is it understandable to you? I also want to have the z component is 2 square root of 2, because this is not any circle. This is a circle at the height of z equals 2 square root of 2. All right, x and y are governed by x squared plus y squared is equal to 1. So these two components are pretty natural to follow. But this one, because your curve is in R3, okay, and t goes from 0 to 2 pi, and then you can easily evaluate whatever this line integral is by using these parametric equations. Okay, you plug in the vector field, and then you take the derivative to each component. You're just taking a single variable integral. Okay, that's what we did on Monday's class. Questions? Okay, so the second part of the problem is I want to take the surface integral of the curve of the function. Okay, surface integral of the curve of the function. Again, no matter it's line integral and surface integral, the key step is to set up the parametric equation, right? Always set up the parametric equation. If in your problem the parametric equations are already given, that's the best news. You can use the parametric equation directly. In most cases, they are not given. They will just give you some conditions. Okay, they will give you some conditions where this surface is, and you need to set up the parametric equations yourself. And this guy is a piece of sphere. We actually talk about the parametric equations of the sphere. Right? It's actually closely related to the parametric equations of the spherical coordinates, right? Once you have the spherical coordinates, you have phi and theta as triangles. The radius is already given, which is 3. You can use phi and theta as your parameters. However, regardless of what equation we have, there's always one way you can set up your parametric equation. We have done this in multiple different cases. There's one universal way you can always set up your parametric equation, which is to set x equals u and y equals v. If in your final integral test, if you're looking at some geometric object, you never heard about the name before, you don't know what the parametric equation is in your mind, you can always go for the usual one. X equals u, y equals v. Are you with me? And then you solve for z. You'll be able to get the parametric equation. So in this particular case, I actually want to practice that way.